Hi everyone, welcome back to another episode of Phys 3500 Classical Mechanics. I'm your instructor, Dr. TJ Hammond. Today we'll be continuing on with Lagrangian and Hamiltonian dynamics, which is chapter 7 in your textbook. So this week we're covering section 7.6 to 7.13 in your textbook. On Monday we showed the equivalence of Lagrange and Newtonian equations. We'd actually already seen this the week before, but we just wanted to formalize this in a derivation to show that the equations of motion you get from Lagrangian mechanics are the exact same that you get from Newtonian mechanics, which means that the physics is the same, it's just a new way of describing or interpreting the physics. That's what we talked about a little bit on Monday, was the kind of the philosophical rather than the physical differences of the two formalisms. We didn't quite finish off looking at symmetries and conservation theorems on Monday, so we're going to continue that today. This comes from, or we can expand on this, and Emmy Noether did, and this becomes Noether's theorem that shows that if you have a symmetry in a system, that's something that's going to be conserved. So we're going to use symmetries in physics to help us simplify problems, and we'll be expanding on this idea today. And the third point that we'll be discussing today is Hamiltonian dynamics. So far we've been seeing that the Lagrangian is the difference between the kinetic energy and the potential energy. I recognize that that's kind of strange because what you've been seeing in a conservative system is that the total energy is always conserved, where the total energy is a total mechanical energy or total mechanics energy, and that is the kinetic energy plus the potential energy. And so it turns out that this is the Hamiltonian, and so we went through that derivation on Monday. Your daily assignment on for today was to convince yourself that any change in this little r vector here is going to be the cross product of the change of this angle here, theta, with this r vector from the origin up to this point. I could try and convince you, and it would take me about 15 minutes to show you that this is going to be the case. But this way, I know that you guys understand this because you've gone and done this on your own. And because it's a three-dimensional problem, it's a little hard to show this in two-dimensional space. So I kind of need you to sit and think about this just to convince yourself that this is going to be true. But we end up using this to show that in an isotropic system that angular momentum is conserved, and we'll be going through the derivation in class. So what we want to talk about also is the Hamiltonian. And so from Monday's lecture, we've found that the momentum of the system is going to be the derivative of the Lagrangian with respect to q dot. That is the time derivative of this position coordinate. And the rate of change of the momentum is going to be the derivative of the Lagrangian with respect to position. So pk is a generalized momentum. So it's either the generalized momentum or the rate of change of the generalized momentum. We'll be writing this as a one-dimensional coordinate, but this will work in any arbitrary generalized coordinate system. And on Monday, when we were deriving the Hamiltonian, we got that the Lagrangian minus the derivative of the Lagrangian with respect to velocity times the velocity ends up being negative, or ends up being a constant, and we call this constant negative of the Hamiltonian. So we also have that from above, this di L by di Q dot is equal to P. So we can replace that here with H is equal to P Q dot minus L. So we've seen that the Lagrangian is dependent on position, velocity, and time, although it is, in this case, explicitly time independent. But now we'll see that the Hamiltonian is dependent on the position, the momentum, in time. And so we want it to be dependent on the generalized position, the generalized momentum, rather than the generalized position or generalized velocity. It's not a big difference, but we'll find that you get some nice symmetries out of it. Oh, this was put in the wrong place. I'll move this slide. So this is to talk about ideas of conservation. We had the conservation of energy before, and that was when we had the system was invariant to time. So we would translate the Lagrangian by some time, and we found that there was no change to Lagrangian. So if that's the case, we have to have total energy being conserved. The conservation of linear momentum came about from when we showed that there was a change in the spatial coordinate, so it went from x to x plus delta x, and we saw that there was no change in the Lagrangian. Then that meant that there was no change to the space coordinate, and that gave us that linear momentum was conserved. And in the third case that we're going through today, if we have the system is invariant to rotations, that means that space is isotropic. So if we, if you rotate your frame by, some certain angle and you see the exact same potential or the same forces, then angular momentum will be conserved. And we saw this last year in Phys 2500, that when we had a central force, so when the potential is only radially dependent, then when you look out any direction from this central axis, you don't see any difference in the potential, then we always had conservation of angular momentum. This should have been in the slide before. Sorry about that. Okay, so talking about the canonical equations of motion, so we have the Hamiltonian is the position, the momentum coordinate times the rate of change of the or the time derivative of the position coordinate minus the Lagrangian. And we want to see how this Lagrangian is dependent on the position and the momentum. So we're going to work through that in lecture. But what we get out is that what are called the canonical equations of motion. That is, di h by di q is equal to negative p dot, and di h by di p is equal to q dot. And they're called the canonical equations of motion because their canon means something as sacred. So people who follow Star Wars very closely, they'll talk about Star Wars canon for some reason, and that's where this comes from. Is if something is like a sacred text or something like that, and so physicists treat this as like a sacred text because they call these the canonical equations of motion, and they're basically called that because they're so nice and symmetric that people think that there must be something divine about it. So what we see then is that the derivative of the Hamiltonian with respect to position is equal to the negative rate of change in the momentum, and the derivative of the Hamiltonian with respect to momentum is the rate of change of the position. So these are the Hamiltonian dynamics equations. So note from before that we had that the Hamiltonian is the total kinetic and potential energy, and that gives us the total energy of the system. And so in a conservative system, the derivative of the Hamiltonian with respect to time is going to be 0. Which we had already seen in Lagrangian mechanics, but I just wanted to point that out here. So the nice thing about Hamiltonian equations of motion is that we have 2 first-order differential equations rather than second-order differential equations that we got from Newton or Lagrange. Obviously, we have to have the same equations of motion from this. It has to be describing the same particle, have the same trajectory, but this is just another different way of describing that motion. So a question for you is, do we want to cover phase space and virial theorem? We won't do that in this lecture, but I want you to think about it. There's 2 optional sections from the textbook. Phase space ends up being fairly important in statistical mechanics, and virial theorem ends up being fairly important to quantum mechanics. So you'll probably be seeing those theorem, or you'll be seeing those subjects in those courses, but I'm just wondering if you want to cover it here so you kind of have a jump on this. It's fine if you don't, they're not going to be on the exam either way. It's just basically if you want to understand these concepts in a classical mechanics setting before we see them in a quantum mechanics setting. Okay, we'll be finishing up the lecture covering example 7.11, and that is when you have the motion is constrained to move on the surface of the cylinder, but you have a force that's always going back to the center of x, y, z equals 0. And we'll see what that equation of motion is.